So let's first quickly discuss the solutions for the quiz and move on with the lecture. Okay, so the first one, it's straightforward. You just apply these rules in this order. You will get the string which is asked for. Okay, so I will discuss only those things which might need explanation. What is the language generated by this grammar? It's a palindrome, right? Whatever character you are generating first, the same character you are generating last. So basically, it's like a mirror image. So you will generate all kinds of mirror images made up of A's and B's. So you will generate all kinds of palindromes with this grammar. The below grammar is not context free because there are two rules here which have terminal symbols in them. Context free grammar never has terminal symbols in its LHS. Okay, it has terminal symbols only in its RHS. In its LHS, it has only non-terminal symbols. Okay, if it has non-terminal plus terminal symbols, that will be context sensitive. We didn't discuss that. Context free grammar has only non-terminal symbols in its LHS. Yeah. So which of these statements are true or false? Sorry. The symbol, this arrow indicates one step and arrow with star indicates 0 or more steps. You know this. So this is straightforward. You need to be careful about whether the arrow has star or not, whether it is being derived in one step or more steps. So that is also important. Like for instance, f derives a in brackets. That is not possible to be derivable in one step because a simple rule, a simple thing for something to be derived in one step is that thing, the thing you are deriving should be present in the RHS of that rule. For instance, if you take f goes to E in brackets or A, so f can derive A in a single step, but it cannot derive A in brackets in a single step. Okay, because A is in the RHS of that rule, it can derive in a single step. So only those things can be derived in a single step where the RHS is present in the corresponding LHS in the rule. If the RHS is not directly present in that rule, then you cannot derive it in a single step. Okay. So you can just test which of these will take more steps. So I won't spend much time on that. What kind of a derivation is this? It may seem leftmost, yes, for the most part of it, but there is one step like this step in which you're not replacing the leftmost variable, but the rightmost variable first. So here expression is being replaced with ID. Here ID should be replaced first. Because in this step, it is not leftmost, the entire thing will not be leftmost. So it is neither leftmost nor rightmost derivation. Okay. Is the following grammar ambiguous? Yes. How do you show that a grammar is ambiguous? More than one parse tree for any string, any sample string you take, you just show more than one parse tree. No, it need not mean every string has more than one parse tree. At least one string has more than one parse tree, and most probably many strings will have more than one parse tree, but it doesn't matter. If there is even one string in the grammar which has more than one parse tree, that grammar is ambiguous. Okay, so let's take an example. Like, so here it is s goes to ss or 0s1 or 1s0 or epsilon. So if I take a string like say 01, 1010, okay, now this can be broken down in two ways, either like this or like this. Okay, so this can be my ss or this can be my ss. So first I apply the rule s goes to ss. So let me derive this first. So here this s again goes to ss, this s goes to 0s1, this s goes to 1s0, right? And this goes to epsilon, this goes to epsilon, and this s goes to 1s0, this goes to epsilon. So you got 0, 1, 1, 0, 1, 0. So here you are deriving this portion first and then this portion. Another way is, so let's try to break it like this. Again, s goes to ss. So this s goes to 0s1, this s goes to ss, this s goes to 1s0, this s goes to 1s0. Epsilon, epsilon, epsilon. Again, you got 0, 1, 1 0 1 0. You see, the string is same, but the trees are different. That's it. So you have at least one string with two different parse trees. Okay. What is the language recognized by the following PDA? This means number of zeros in W, and this means number of ones in W. So the thing is straightforward. You see, in Q1, whatever symbol you are getting, you are pushing it onto the stack. That's it. In Q2, whatever symbol you are reading, it doesn't matter. You are popping one symbol from the stack. Whether you are getting a 0, you are still popping whatever is there on top of the stack, 0 or 1. Whether you are getting a 1, you are popping whatever is there on top of the stack, 0 or 1. It doesn't matter. So for every symbol you are reading, you are popping one symbol from the stack, independent of whether the symbol you are reading and the symbol on the stack are same or not. Okay? It only means the count of the remaining symbols you are reading should match with the count of the symbols on the stack, which means the symbols that you pushed already, that is in the first half of the string, should be equal to the number of symbols you're reading in the remaining second half. Okay. Now the only thing is the middle one. So this basically says the middle symbol should be 0. That's it. So basically this says you should read an odd length string with a 0 in between. So let me take an example. Suppose if I am reading some string, say 10011. Now say the stack will start with $1. Now it is at this one. I will pop this. I will push this one. So first I will take the correct branch, assuming it can take many branches. Okay. So I will show you the correct branch path. Now it is reading this 0. I will push that also onto the stack. Now it is reading the second 0. What I will do, I will skip it. So this transition, I am reading a 0 and I am skipping it. I am doing nothing with the stack. I am neither pushing nor popping. I am skipping and going to Q2. Okay. So I am at this 0, but I am skipping and going to Q2. The stack will remain the same. Okay. Now I am at this 1. Now I'm in Q2. Okay. Now whether I am getting a 1 or 0, I am popping the symbol from the stack. So I am reading this 1. I am popping this 0 from the stack. So the stack will become $1. Now I am at the last one. I am reading a 1. I am popping whatever is there on top of the stack. I'll just pop it. It doesn't matter. Now the stack will become $. Finally, done. You reach the end of the string. You will pop the $. That's it. So that you reach the end of the string. The stack is empty. Done. You accept it. Okay. But suppose I take a different branch for the same string. 10011. So I'm in Q1. I am reading a 1. I'm pushing it. Okay. So say I start with $10011. I am in Q1. Say I push it onto the stack. Now I am reading a 0. Now instead of staying here and pushing this 0, I will take this branch. Okay. Now what will happen? I will do nothing. I will just go to Q2. So the stack will remain the same. I'm basically skipping this 0. I'm going to Q2 with the same stack. Now I'm reading the next 0. Okay. Now I'm in Q2. Whatever symbol I'm reading, it doesn't matter. I'm popping a symbol from the stack. So I pop this 1 from the stack. I'm left with $1. Now I'm reading this 1. Okay. Now I'm reading a 1, but there is neither 0 nor 1 on top of the stack. So this state does not know what to do. The only option you have is to see this. You have $1 on top of the stack. So pop it. So I pop this $1 from the stack becomes empty, but still the string is not empty. I still have a 1 left. I don't know what to do with this 1. It is not defined here. What to do when the string is not empty yet. So it will reject it. Okay. So this branch will be rejected because this 0 you skipped and went to the other half of the PDA. But this 0 is not the middle 0. That is why this branch will be rejected. The previous branch is accepted because this 0, it is okay to skip because this is the middle 0. So the first half you are pushing. When you're reading the second half, you are popping the first half. In between, you need a 0. That's all. So basically, it is an odd length W with 0 in between. That's all. It should not have 1 in between. Even then it will be rejected because it is taught only to skip 0. If it sees a 1, it doesn't know what to do. It will just reject it. Okay, so that is the thing. So it's a it's not a palindrome. Sorry, it's not a palindrome. It's just an odd length string with 0 in between. Okay. This is the exact same problem which we discussed in the class. Equal number of zeros, ones, and 1 zeros. That same thing I just replaced with CDs and DCs. That is a regular language. We already discussed this, so I won't discuss it again. This is also straightforward. A is the symbol to be read, B is the symbol to be popped, C is the symbol to be pushed. That's it. And L equal to WWR. What kind of a language is L? This has to be context-free language, because to compare W and W reverse, you have to push W first and you have to store it. And that storage is possible only in PDA, not in FSM. So it's not a regular language, but a context-free language. Okay. And this is also straightforward. It has more ones than zeros. Like for instance, if you take these rules here, it will produce equal number of 0 ones and 1 zeros, right? But here it will produce at least one extra one. And similarly here also it will produce at least one extra one. So it will have more ones than zeros. Fine. Okay. This is a palindrome, right? Again, similar to the previous case. In the first half, you are pushing whatever you are getting, 0 or 1. In the second half, you are popping. You are doing conditional popping. When you are getting a 0, if 0 is on top of the stack, you pop it. When you are getting a 1, if 1 is on top of the stack, pop it, right? Which means whatever symbol you got, say at the beginning, that same symbol, if you are getting at the end, then you are popping it. So they should match. So the symbol at the beginning should match with the symbol at the end, and so on. Okay. And in between, why do we have this? Can anyone tell me? Yeah. Anyone else? Why do we have this transition? This we understood. This we understood. Why do we have this? Right. So you can have even length string or you can have odd length string. If the string is of odd length, then you will have one symbol in between. So that can be anything. It matches with itself. The left of the string should match with the right of the string. The middle symbol can be anything. So that is what is covered here in 0 or 1. So the middle symbol can be 0 or the middle symbol can be 1. That is for odd length strings. For even length string, the middle symbol should not be there. Left half and then immediately right half. So epsilon. There is no middle symbol. That's what epsilon is indicating. Okay. So you should slowly learn how to look at a PDA from a high level. You should understand a PDA from a high level. Any doubts? You understood what I said? Okay, so this covers all three cases. This covers all different kinds of palindromes, even length palindromes, odd length palindromes. If I want only even length palindromes, then this 0 transition and 1 transition should be removed. Only epsilon should be there. If I want only odd length palindromes, then this epsilon transition should be removed. Only 0 transition and 1 transition should be there. If I want to cover all length palindromes, then all these 3 transitions should be there. Okay, so that's the idea. This is straightforward. You just check which strings are derived. You can test it on your own. Okay, select all the false statements. A context-free language can be recognized by a non-deterministic finite automaton. False. You need a pushdown automaton, not an NFA, to recognize context-free language. If M is a DFA that recognizes language A, swapping the accept and non-accept states in M yields a new DFA recognizing the complement of A. This is a true statement. Although we didn't discuss this explicitly, this is if you had, while preparing for minor 2, if you had gone through the textbook, the problems and exercises at the end of the chapter, you will know this is true. Okay, there are some problems which discusses this. So basically, this is a true statement. If you are given a DFA which accepts a language, you can build a DFA which accepts the complement of that language just by reversing or swapping the accept states with non-accept states in the DFA. That's it. In terms of recognizing power, DFA equal to NFA less than deterministic PDA equal to non-deterministic PDA. This portion is correct. DFA is equal to NFA. Less than is also correct, but this portion is wrong. Deterministic PDA equal to non-deterministic PDA is wrong. Deterministic PDA is also less than non-deterministic PDA. Okay. NFA is equal to PDA plus stack. Wrong. It's the reverse. PDA is equal to NFA plus stack. A push-down automaton is not a finite automaton since it has unlimited number of states. That's wrong. Not because it has unlimited number of states, but because it has unlimited memory. Okay, so that is the difference. So this statement is also wrong. Is the following grammar unambiguous? No, it is ambiguous grammar. We discussed this already, so I won't discuss it again. What is the language recognized by the following PDA? It is, it has more ones than zeros. Some of you may mistake this with that the last symbol is 1. No, you see that, the last symbol is epsilon in some sense. If this epsilon were replaced with 1, then the last symbol will be 1. You're not reading 1 here, you're popping a 1. And what is the, when we are saying you pop many symbols in between, at the end you're popping 1, what does it mean? You pushed 1 in the beginning somewhere, which means 1 you read long back. So last symbol is not 1. 1 would have been somewhere in the beginning. Okay. So some symbol which you pushed long back, which you read long back and you pushed long back, that symbol you're popping now. Okay. So last symbol is not 1. In fact, 1 would have been one of the first symbols. Okay. So what does this say? Basically, what does this transition say? This basically says, if you are getting a 1, you pop a 0 if 0 is on top of the stack. If you are getting a 0, you pop a 1 if 1 is on top of the stack. Otherwise, push that 0 or 1. This is equal to what? PDA. Number of ones and zeros are equal. This PDA up to this portion, ignore the last transition, up to this portion, this PDA handles languages with equal number of zeros and ones. Okay. Now we are saying you are popping an additional 1, which means the number of ones in the stack are more than the number of zeros in the string. Right? That's it. So the string contains more ones than zeros. Fine. You got it? That's it. Okay. Okay. Is the following grammar unambiguous? No. False. Again, you can generate a string, something as simple as AAB is ambiguous. So it is AB or AAB, and A goes to AA or A, B goes to B. So if you take a string like AAB, this will have two parse trees. That is, S goes to AB, A goes to AA, B goes to B, A goes to A. This is one parse tree. Another parse tree is S goes to AAB and B goes to B. Same string, two parse trees, ambiguous grammar. That's it. Which of the following languages is generated by the given grammar? It is AB whole star or A union B whole star. So this is not like A star B star or A power n B power m. No. Why? Because what does this do? This generates any number of A's. This generates any number of B's. Now you can mix them in any way. Generate any number of A's and generate any number of B's followed by any number of A's followed by any number of B's and so on. You will get all possible combinations of A's and B's. That's it. Okay. And what is the language generated by this grammar? The answer is the fourth one. So the string can be broken down into two parts, X and Y. X and Y lengths are equal. So two halves where the first half is not equal to the second half. Why? Because you see AB and BA, you can think of them as say XAX, XBX in the sense, suppose AB and BA, their lengths need not be, actually, yeah, they will be equal because those are the only options you have. Now, even if their lengths are equal, you will have A in between here in one of the halves and B in the other half. In one half, if you have A, in other half, you will have B. And A will always be replaced by 0, B will always be replaced by 1. So there will be at least one character at the same position being different with respect to the same character in the other half. Right? So if I say S goes to AB, A goes to XAX, B goes to XBX. Okay. Now they will be of same length because X can be only 0 or 1. X can be only 0 or 1. Let's assume this X is equal to this X and this X is equal to this X. But this portion will be different because A will always be 0 and B will always be 1. So you will have at least one symbol different in the first half and the second half at the same position. Okay, that's it. Yeah, last one. This is an ambiguous grammar. Why? Like you have take these two statements: if statement and again if statement, else statement. Okay, so I have like two things: if statement and then if statement, else statement. Now let me take an example of a nested if else statement. So I can have a statement like if statement, else statement. Okay, so this is like a nested if else. Now this can be broken in two ways. Either I can group this as one unit and say if statement, else statement. Okay, or I can group this entire thing into one and say if this entire statement. In the previous case, else was associated with this, but in this case, this else is associated with this if. You got it? In this case, this else is associated with this if. In the previous case, this else is associated with this if. So same statement, you can parse it in two ways. So you will have two parse trees. So this is an ambiguous grammar. Okay. Yeah. Let's move on. So let's start the next chapter. That is Church-Turing thesis. So how can we end this course without discussing Turing machines? Okay. So let's try to understand a Turing machine by comparing it with the other machines that we discussed. So what is an FSM? An FSM is a machine with limited memory. A PDA is a machine with unlimited memory but with restrictions. So can anyone tell me what are the restrictions in PDA? Yeah. What are the restrictions on memory in PDA? The memory is of stack nature. That is, you can access only the top element anytime. You can't access the below symbols, and you can't, read, write, all those things. You can only pop or push. That's it. And you can access only the top element. So the memory, only stack kind of memory is allowed in PDA, not queue kind of memory or circular queue kind of memory or any other kinds of memory are allowed in PDA. Only stack kind of memory is allowed. Okay. So last in, first out format only. Whereas a Turing machine is a machine with unlimited and unrestricted memory. Okay. We'll see what that is in a while. In terms of power, FSM is less than PDA, which in turn is less than a Turing machine. Okay. A Turing machine can do everything a real computer can do. But there are some problems. Beyond the theoretical limits of computation. Hence, a Turing machine also cannot solve them. For instance, halting problem. We won't have time to discuss this. You can look it up online, or I briefly mentioned it in the beginning of the course. Does anyone remember? Yeah, what is it? I don't remember. Anyone?
We are not able to design a meta program that is when to stop like
A meta program that?
we can't design a meta program that will tell the program to stop at a point like this. We won't be able to design a meta program that will tell a program when to stop.
Okay, okay. It's not exactly that. So suppose I have a program like, suppose I have a program which adds two numbers. Okay. Now this program, we know that it takes, if two numbers are given to that, it will print the output and stop. Okay, that is one way. Another way is, say, instead of numbers, if some strings are given to it, it will raise an error and stop. Okay. In either case, it will stop, it will halt. So halting does not necessarily mean only ending in an accept state. It can end in an accept state or a reject state, but the point is that it ends. Okay. But suppose I am given a program which either intentionally or unintentionally ends in an infinite loop. Okay. So for instance, if I take an example like say scan n, and I write a for loop for I instead of n, yeah, it's okay. For I equal to n, I equal to 0, I equal to I minus 2, whatever, I write something inside. Okay. Now, does this program halt every time? No. When does it not halt? When n is? Yes, when n is negative, or when n is odd, right? The only case where it halts is when n is even and n is greater than 0. Okay. So just by looking at the program, we don't know whether it will halt or not. Somehow we, as a meta program, in this particular example, we somehow know that, okay, it halts on these inputs, it does not halt on these inputs, right? But to a normal eye, it seems okay, syntax is fine. Yeah, if n is greater than 0, it will halt, it will reach 0 at some point, so it will halt. No, there are cases where it will not halt. There are cases where it will halt, but there are also cases where it will not halt. Okay, so we need to sort of imagine every possible case where it will halt, where it will not halt, and that is for one problem. Okay, now imagine I have a meta program which tells me any program on any input whether it halts or not. There is one meta program which can take a program and an input as a pair, and it tells me whether this particular program halts on this particular input or not. Such a meta program is not possible. That is what Turing proved. That is the halting problem. Okay, he basically said halting problem is undecidable. Okay, so we'll not get into that. You can check the textbook later sections, or you can look it up online. It's a famous problem. So that is a big blow to Hilbert's project, that mathematics is formal, everything can be derived or everything can be decided. You can at least decide whether some problem is provable or not, although you cannot give the exact proof whether it is provable or not. So that is disproved by Turing. That is halting problem, and in the process of that, he invented Turing machine. That's the idea. Okay, so let's not spend more time on that. Let's move on. Okay. Parts or actions of a Turing machine. So a Turing machine also has a state control. It will also have a state diagram. And it has an infinite length input tape. So your input will be on this tape, followed by blank symbols. Blank symbols are represented like this. And there is something called a read-write head that reads the symbols on this tape and also overwrites them. We will see that. Okay. So there is an infinite tape with closed left end and open right end. Now you may get a thought that this also seems to be restricted memory, right? That one end is closed, only one end is open. What if both ends are open? Maybe that will be more unrestricted. Again, later sections, which we will not be able to cover. In the textbook, there is a section called variants of Turing machines, where he discusses a variant where both ends of the tape are open. And he will show that that is not more powerful than this. That is as powerful as this only. Okay, so whether one end is open or two ends are open, both are equally powerful. Here, infinity is the important thing, not whether one side infinity or two sides infinity. This is infinite, and this can do everything that a both side infinite tape can do. Okay, so it is unrestricted in that sense. Okay, and input symbols on the left end of the tape followed by infinite blank symbols. And we also have a read write head. So it can not only read or scan the symbols on the tape, but also overwrite them with different symbols. And can move left or right one step at a time. Okay. The Turing machine continues computing until it enters an accept or reject state. So a Turing machine has accept state, only one accept state, and also a reject state, a separate state called reject state. Whereas in FSM or PDA, we don't have a separate state called reject state, right? We only have accept states. Okay. A Turing machine has a separate state called reject state. It may also happen that it never enters an accept or reject state and go on forever in an infinite loop, never halting. So like I said, halting does not mean it should end up only in the accept state. Halting may mean it can end up in the accept state or it can end up in the reject state. Anything is halting. But there can be a third case where it will never halt. It will go on in an infinite loop. It will neither go to the accept state nor the reject state. So that is the non-halting state. Okay. So there can be no machine which tells me whether any program halts or not on any given input. There can be no general program. There can be no generic algorithm which handles all these cases, because each one is a different case and you need to write different algorithms for different cases. There can be no one single meta program that tells you whether this program halts on this input or not. Okay. All right. But if it enters accept or reject state, without waiting for the input string to be finished. Can one of you close the door? Unlike FSM or PDA. In FSM or PDA, what do we do? Even if we reach the accept state, we still wait for the input string to be finished, only then we say it is accepted or rejected. Okay, whereas here, if we enter the accept state, done. No more need to read the input string. Similarly, if we enter the reject state, done. No more need to enter the, no more need to read the remaining input string. Okay, that's it. So accept or reject states take immediate effect in a Turing machine, unlike FSM or PDA. So let's look at an example. Construct a Turing machine that recognizes the language L equal to W hash W, where W belongs to 0, 1, O star. Basically, this is over 0, 1, over sigma equal to 0, 1. You build a Turing machine that recognizes the language W hash W. Now you see, this is not like W followed by W reverse. This is W hash W. So can this be solved using PDA? No, because here you need to read the bottom of the stack. If you are pushing the first half of the string onto the stack and the second half, you are not comparing the first symbol of the second half with the last symbol of the first half. You are comparing the first symbol of the second half with the first symbol of the first half, which means you need to access the bottommost symbol of the stack. That is not possible in PDA. So you can't use the stack structure here. So you have to use a queue structure, right? That is possible in a Turing machine. Okay, so that is this is an example where PDA cannot do the job, right? So first, let's discuss the algorithm. So algorithm for Turing machine, say M1. Zigzag across the tape to compare the corresponding symbols on both sides of the hash. if there is no hash symbol or the corresponding symbols reject. Cross the symbols as you read them to keep track of which symbols correspond. So basically, assume you have an input string, right? And you have a hash in between. Now what do? We first look at the starting symbol. Then we move to the right until we see a hash. And then we cross the hash. We look at the first symbol on this side. We compare these two. Okay? If they are correct, fine. I mean, first you cross this symbol. If it is, you remember the symbol that you read. If it is, and then you read the second symbol after the hash. If both are same, cross it. Now come back again, move left. Back to the beginning portion until you see a cross. The symbols you crossed, stop there. Now read the next uncrossed symbol. Now again, cross over hash and read the next uncrossed symbol. Match them, come back, read the first uncrossed symbol, match it with the next uncrossed symbol, and go on. Do this in a zigzag fashion. If every symbol you have crossed and you see a blank, it means it is a proper string. But if any symbol is not matching, or if you don't see a hash, it is an improper string, an invalid string. Okay. So there's the first step when you reject, and when do you accept? If by the time all the symbols in the left half are finished, the symbols in the right half are also finished, accept. Else, reject. Okay, so we'll look at the example tomorrow. Right now, this is the algorithm. Okay, so like I said, this is not possible to be recognized by a PDA because it is not about W reverse, it is about W hash W. So a stack cannot help you in this case. You have to use a queue kind of a thing, right? So that's possible in a Turing machine, but not a PDA. Okay, so let's stop here.